first with magnetism. What is magnetism? Well, magnetism refers to the magnetic force. Magnetic force is a force, as the name would imply. And just like all of the other forces, it's a vector, meaning it has a magnitude and direction, and it has units of newtons, just like applied force, friction, tension, all of those other forces that we talked about. Magnetic force is the same. It's a vector, magnitude and direction, and units are newtons. Okay. This force, it arises from the movement of charged particles. Like, for example, charged particles moving through a wire, right? That's a very common way to get magnetic fields and magnetic force. Okay. The formula for the magnitude of this force is equal to F equals QVB sine theta, where F is the force, right? It's the magnitude of the magnetic force. Q is the charge of the moving particle. V is the velocity of the moving particle. B is the magnetic field, which we'll talk about in a bit. And theta is the angle between the velocity and the magnetic field vectors. Both magnetic field and the velocity, are vectors, just like force is a vector. And so if there's a 90-degree angle, 180-degree angle, that's what you would put in the sine theta. Okay. And if they are 90 degrees perpendicular, you can sine theta is 90, and then it just becomes 1, and you can just kind of get rid of it. You can ignore it, right? Because sine 90 is 1, so 1 times anything, you can get rid of the 1. Okay, the direction of the magnetic force, you can usually very simply find it out using the right-hand rule. And here's a diagram of the right-hand rule. And there's actually another right-hand rule that we're going to cover in this lecture. This is just remember, this is a different one, right-hand rule. It's with the 3 fingers, right? And so if you just put your right hand, right, it has to be the right hand, otherwise it'll be wrong. Then you have your 3 fingers going like this, in the same way that it has here. You have this one going this way, this one going this way, like towards, and then your thumb going up, right? So the thumb is the direction that the force is going. The magnetic field is this finger, and the electric current is this finger. Essentially what this you can do is you can move it any way you want, depending on how it's drawn on the paper. So for example, if it says the electric current is going this way, magnetic field is going this way, which way is the force going, for example? Well, you can just make a right hand, magnetic field, electric current. So you just have to line it up, magnetic field, electric current, and I know it's hard to see because the screen is kind of breaking, but you can kind of just move it this way, your right hand, and then it'll show you which way the thumb is pointing, and that's the direction of the force, right? Just rotate your hand in space after making this sign. And you can very easily find the direction of any of these 3. Okay. All right. And some of you know that this is a general rule that you can really do for all vectors when you are multiplying vectors. We haven't really come across it that often, but this is really one of the only things that we use it to come across. So this is a great way to just for all vectors, when you multiply, do vector multiplication, the same right-hand rule applies. All right, next we talked about it, magnetic field. So magnetic field is a field of vectors, and it describes how the field, any charged particles within the field get affected by it, right? And the main thing that we see, there's multiple different sources that can produce magnetic fields. For example, magnets, looped coils, the Earth also produces a magnetic field, wires, obviously, both straight wires and curled wires, like looped wires. There's many different types of things that produce a magnetic field, and all of the magnetic fields pretty much are different of how they look, right? Depends on the object. The 2 most common that we usually see, at least for the MCAT, and I think probably in your general physics class, is magnet, like a bar magnet, and a single straight wire. Okay. And I've shown pictures of both of them right here. So the bar magnet always has these lines going from north to south, and they just go like this, like this, going straight in, and like this. You get the picture, right? From north to south going. That's on a bar magnet. That's the direction of the magnetic field, at least. And this is the other right-hand rule that I was talking about, the curl right-hand rule. Essentially, make a thumbs up or like a curl with your fingers, just like how it's shown there. Again, it has to be the right hand, otherwise the direction will be wrong. And then the direction of the current flow is just the wire, right? So if you have a straight wire, like you can see here, your thumb has to be on the way the wire is. So if the wire is like this, your thumb like this, going with the wire, and then the magnetic field is around based on how your fingers curl, and it's going this way, right? It's going where your fingers are curling like arrows, essentially. Yeah, and remember, it has to be the direction of current flow. So if current is flowing from bottom to top, it's like this. It's going from top to bottom, it's like this. And the current and the magnetic field is going this way. Okay. So remember, it's right-hand rule. Fingers, thumb points towards where the current is flowing. Fingers curled point to where the magnetic field is pointing. Very simple. The magnitude of a magnetic field is usually measured in either Teslas or Gausses. Typically, I think mostly I've seen Teslas, which uppercase T. Gauss is like a small unit. It's kind of like ounces and like pounds, or like nobody really talks about in ounces in real life. Mostly you talk about pounds because ounces are kind of small. Same thing with Teslas and Gausses. I think the conversion is like 1 Tesla is like 20,000 Gauss or something like that, but I could be wrong. But it doesn't matter too much. They'll give you the units, right? A Tesla is equivalent to a Newton per ampere meter, right? That's the standardized units using units that you would know. Again, remember the equation that we used before. The F to get magnetic force is force equals to QVB sine theta. What we can do to find the units is we can turn these units, we can turn this equation into units, sorry. And if we do that, we get newtons, because force is in newtons, equals coulombs, because charge is in coulombs. Velocity, you know, is in meters per second. Magnetic field is unknown. I'll just put x because this is what we're trying to find. And sine theta is just, it's unitless, right? It's an angle. So we can get rid of that. So we have this equation, and we know left-hand side, right-hand side must be equal. Therefore, we know that this x, which is this magnetic field, we don't know what these units are, right? It's a Tesla, but what does that mean? What is that? In order to find that, we can essentially just find out how we can make the left and the right. We know that we need to have a Newton on the left, so that means we need to have a Newton on the right. So that means x has to have a Newton on the top, right? Because you need to multiply the right side by newtons. Okay. Now you need to divide the left side by both coulombs and meters, right? You need to divide by both a coulomb and a meter, because you need to cancel these out, right? And then you need to multiply by seconds, because you need to cancel this out. And then if you do that, if x is equal to this, then meters will cancel out, seconds will cancel out, coulombs will cancel out. You're only left with a Newton, which is the final answer, which is what it is equal to, right? That's how you would derive a unit. And the reason I'm telling you all of this is it doesn't really have to do with magnetic field, really. But this can be useful on the MCAT, because they may give you unit questions. Like, for example, they may give you something like this, and then they'll ask you which of these answer choices is equivalent to this, and they'll have like things like amperes. They'll have things like all sorts of things, like just replacing these like newtons, replacing these coulombs, replacing these meters per second with other units that kind of used very specifically, but they're equivalent to some of these, and they'll say which of these are equivalent, and you have to do something like this where you kind of have to figure out which of these units kind of cancels each other out and what kind of makes this, right? So this is something that I've seen before. Okay, and since we're left with this, so Tesla is equal to this, we notice we can actually simplify this further, right? Because you know that a coulomb per second is an ampere, right? Because current, which is I, is just equal to charge per second. Units for current, amperes. So that means an ampere is equal to a charge per second or a coulomb per second. So we have the opposite. We have second per coulomb. Well, what do you do with that? Well, you just invert it and you just get 1 over ampere. So you can cancel this out, cancel this out. You're left with Newton times 1 over ampere times meter. You can just erase the 1 because obviously it doesn't matter. So finally, you're left with newtons per ampere meter, which is what I said that Tesla is officially equal to. Okay, and that's how you would derive. That's how you would do unit derivation. And again, not related really to a magnetic field, but it's something that may come up on the MCAT, and I think it is very useful for you to know units and unit derivations. So whenever I get the chance to do with physics, I usually try and incorporate a little bit of unit derivation in each lecture. Okay,